Now we want to prove the hard direction of Landau's theorem. And that's going to rely on the team version of Hall's marriage theorem. So we're going to start by just recalling that. Okay, so previously we discussed this in terms of a job allocation problem, but now we're going to just try and restate the theorem in a kind of slightly more abstract way. The same result, but just kind of without some of the baggage of job allocation stories and so on. So suppose we have finite sets A and B. So in the story we told before, A was the set of people and B was the set of jobs, but they could be any finite sets. And for each J and B, a number Mj, non-negative integer. So in the previous story, that was the team size required for job J, but could be any number. And a subset Cj, subset of A. So again, in the previous example, Cj was the set of people who were qualified for job J, but again, in this abstract formulation, could just be any arbitrary subset of A. So for any subset U of B, we're going to put, well, firstly, mu is the sum over J and U of Mj. So in the previous example, that would be the total team size required for the jobs in U. And Cu is the union over J and U of the set Cj. So in the previous example, that would be the set of people who are qualified for at least one of the jobs in U. So what are we trying to do here? Well, we want to try and choose disjoint subsets Tj of A for J and B. Right. In the previous example, these Tj, this would be the team of people who's allocated to do job J. And they're supposed to be disjoint subsets because no one is supposed to be allocated to more than one job. So the size of Tj should be equal to Mj. So again, we've got teams of the right size, and also Tj is supposed to be a subset of Cj, which in the previous example is just the condition that we're only allocating qualified people to these various jobs. And then the theorem says this is possible if and only if we have this plausibility condition that the size of Cu is greater than or equal to mu for all U. Okay. So that's our team version of Hall's marriage theorem. Okay. And so now suppose we've got a potential score sequence. Okay. And remember that means that so in particular that means that the sum of the SIs is n choose 2. And we're going to assume that we have the plausibility conditions hold. Remember, so there were 4 different versions of the plausibility condition, and they're all equivalent. So we're just going to mention the one that's going to be most useful here. Plausibility condition is going to be that SU is less than or equal to K choose 2 plus K n minus K So any you've got any set of k indices, then the sum of the corresponding u's is SU. Yeah. So so the sum of the corresponding SIs is got to be less than or equal to k choose 2 plus k times n minus k. Okay. So Landau's theorem claims that in this case it's possible to find a tournament whose score sequence is this sequence S1 up to Sn. And we're going to prove that as an application of Hall's marriage theorem. So yeah, so we need to kind of set up a matching problem as we were discussing in the context of Hall's marriage theorem. So we're going to take B to be just set 1 up to n. So that's supposed to be the players in our tournament. And we're supposed to be setting up a tournament. We want to show that this sequence is realizable, so we want to set up the tournament in such a way that player I gets a score of SI. So A is going to be the set of medals, okay? So what this kind of really means is a set of subsets of P. Subsets of size 2 in B, right? And so each medal kind of names a pair of players, or you could say A is just a set of matches if you want. Okay. Okay, and then we're going to put MJ as SJ. So yeah, remember in setting up the team version of Hall's theorem, we need to know these numbers MJ, which are kind of like the team sizes needed for the jobs. Okay, so we're just going to take MJ to be SJ. And then we also need to take CJ is the set of medals naming player J. Okay, but medal just corresponds to the pair of players that are named on it, so this kind of corresponds to the sets of size 2, where one of the elements of the set is your J. Okay. So we need to, so this gives us a team allocation problem, and we need to check that it satisfies the correct plausibility condition. Okay. Okay, so we've got these, you have to consider these numbers. MU is SU, so MJ is SJ, so MU is SU is the total of scores. Players in U. And CU is the union of all the CJs. So that's a set of medals which can name at least one of the players in U. Okay, it's so if mod U equals K, if there's K players involved, then size of CU is going to be K choose 2. This is kind of a case where both names are in U. Plus K times n minus K. Okay. Okay, so this is for one name in U, one not. Okay. And this is greater than or equal to SU. That's by this assumption. Okay, we're assuming that we were assuming that this potential score sequence that we started with satisfies the plausibility condition, which is that SU is less than or equal to K choose 2 plus K times N minus K. So that's greater than or equal to this thing here, which is MU. Okay. So the whole plausibility condition is satisfied. Okay, so that means so the plausibility condition is satisfied. So therefore, allocation is possible. So we've got a solution for the allocation problem. We can set so we can choose a set Tj of Cj. We can choose disjoint sets. Tj sub Cj for each j. So with each Tj, size of each Tj is going to be equal to Sj. Okay, so in other words, so this is a set of metals. So we say that player J wins all the medals in Tj. Wins the corresponding matches. Okay. Notice incidentally, so these sets Tj, they're disjoint, and so and the sum of the sizes is the sum of all the scores, which is n choose 2. So that means that the union of the Tj's has to be the full set. Has to be the full set B. So we've got allocated all the medals now. Okay. So this specifies a tournament with score Sj for player J. Okay, and so that's what Landau said was possible. Yeah, the fact that we've got such a tournament means that the score sequence is realizable, and that was the supposed conclusion of Landau's theorem. So now we've proved Landau's theorem on scores in tournaments.